Hello, everyone, and welcome to the E3SM All Hands webinar. And this week we have Rob Hetland, who's at PNNL, and he's going to be telling us about the SEAHORCE project, which he's a PI for. He's also a PI for Compass GLM and a co-PI on the ICOM project. He joined us at DOE in 2021. Before that, he was a professor at Texas A&M, where he studied a wide range of coastal physical and biogeochemical processes, including the dead zone in the northern Gulf of Mexico, harmful algal blooms along the Texas coast, and sub-mesoscale processes within the Mississippi and Chapalaya River plume. Thanks a lot, Rob.
All right, thanks, Mark. All right, I'm assuming this looks fine to you. You can see the presenter mode.
Yes.
This talk is on a relatively new SADAC 5 project, study for exascale advances in a high-resolution ocean using ROMS coupled to E3SM, and we call it SEAHORCE with a little thing on the C to make sure it's pronounced correctly. My collaborators are Ann Almgren from LBNL, who's working on ROMS X development, Darren Inguerda from Los Alamos, doing E3SM and MPASO coordination, two collaborators from ANL working on MOAB coupler development, and we have a university partner, Harper Simmons, who recently moved from Alaska to UW-APL, and he is our regional modeling lead. We are using some of his realistic domains in this project. I'll explain what these components are soon. So our SEAHORCE project, to get an overview of our objectives, are to focus on improved representations of small-scale coastal and open ocean processes, such as river plumes, coastal fronts, and sub-mesoscale eddy processes in the context of global Earth system models. And to do that, we're looking at nesting ROMS with an MPASO. So we're going to create a framework for two-way coupling between ROMS and MPASO for optimal, flexible, efficient, and robust dynamical up and down scaling. Since two-way coupling is more complicated than nesting, we would get one-way nesting kind of for free with this approach. And another aspect of the project is we're creating a version of ROMS. And if you've never heard of ROMS, ROMS stands for the Regional Ocean Modeling System, and it is a community coastal ocean model that's been in development for 20 plus years. And it's sort of a standard for coastal applications, certainly within the US. It's based on Fortran. We are creating ROMS X, which is a port of ROMS into C++ that will allow us to run on GPUs that can exploit the latest DOE Exascale high-performance computing architectures. And so these are the general project outlines that we have, project objectives that we have. So I'd like to start with a little motivation for why we want to do this. And so here's an example of dynamics across scales with MPASO. Traditionally, climate models have been, by necessity, fairly coarse resolution, being a degree or half degree. And so here's an example in the Gulf of Mexico. The Chapalaya River comes in right about here. No, that might be terrible. I think it comes in right about here, just so you know. So traditionally, these coarse models don't show prominent features in a region like the Gulf of Mexico, with this loop current coming in here. This is an extension of the Gulf Stream that comes in, and this loop will form eddies that break off, and then will propagate westward and hit the Texas-Mexican coast. So this is a fairly important piece of the ocean variability in the Gulf of Mexico, and 30-kilometer, which would be equivalent to E3SM low resolution configurations, doesn't really have a loop current or a loop current eddies. When this is run under what would a 10-kilometer regionally refined simulation equivalent to the E3SM high resolution config, you get some eddy features like you can see here in the surface temperature, but they're fairly weak. Now, so here you see the surface temperature, so the warm water of the Gulf, the loop current and the Gulf Stream. Here, down here, we're showing the surface relative vorticity, which is a Another way to think of this is it's F times the Rossby number. So if we normalize this by the planetary vorticity, we get the Rossby number. So where you see red, these features are fairly energetic and high Rossby number, meaning they can be nonlinear. These are weakly nonlinear. So the flows in this are still mainly large scale, geostrophic, mesoscale flows. Darren and Weirda recently ran a 2-kilometer configuration, regionally refined, and you see that there are sharper fronts, instabilities forming within the fronts, and there's a whole new class of features that are developed, and the relative vorticity proportional to the Rossby number increased, indicating that these are much more nonlinear features, not necessarily governed by geostrophic, large-scale linear flows. I'll be talking about sub-mesoscale features a lot in this talk, so I just wanted to provide a quick definition. So sub-mesoscale, we often think about it just in terms of a length scale, but really it's a dynamical scaling that depends on stratification and the flow conditions. And so sub-mesoscale can be characterized as a Rossby number of 1 and a Richardson number of 1, whereas mesoscale, larger scale things, are Rossby numbers much less than 1, meaning fairly geostrophic, linear flows, and Richardson numbers much greater than 1, meaning fairly stably stratified. Or another way to think about it is sub-mesoscale flows are anisotropic energetic instabilities. Sub-mesoscale permitting simulations with an MPSO position us at the forefront of contemporary, very high resolution global ocean modeling. This is really a great feat, but these simulations are really expensive. So the 2-kilometer simulation represents the highest baroclinic MPSO simulation to date, and it is you can do 96 simulated days per day using 12,000 cores on NERSC. So a spin up requires about 3 weeks of wall clock time, and even then, as we'll see in some subsequent examples, are these sub-mesoscale dynamics well enough resolved? They're permitted, but not quite resolved. And so we're kind of at the border of being able to resolve, the details of these energetic circulation features. So you could expect, as you double have the resolution, double the number of grid points, you can expect a 4 to 8 times slowdown. I always think about it as an order of magnitude slowdown for each halving of resolution to achieve 1-kilometer resolution. And so that's, we're talking a lot now to do a quick 5-year spin up. And in coastal applications, the state of the art for ROMS applications is to employ order 100-meter resolutions to capture these sub-mesoscale effects. And so we're still a long ways away. So there are limits to how far we can refine resolution with MPSO, and it will be a long time before we are able to really capture these small scale mixed layer instabilities or coastal sub-mesoscale processes. However, this E3SM high resolution configuration actually does efficiently span between sort of the mesoscale permitting space for global climate modeling. And this, for the first time, allows us to meaningfully couple to coastal or sub-mesoscale models. And I think this is a very big point that if you were in the global modeling community, you might have seen sort of a gradual transition toward higher and higher and higher resolution. But I believe that from the coastal ocean modeling perspective in particular, that this resolution crosses a threshold where we can start to use these results to nest higher resolution models within. And this is a big deal. And so, I'm excited to use these results in my coastal projects like Compass, GLM, and ICOM. And I think there's a lot of other people in the regional and coastal communities that are excited to use this new class of models that are being developed, because we can now much more meaningfully transfer information to smaller scales. So we think that a targeted and temporary and stealth nesting or coupling approach is reasonable considering these things. So, scientific questions may be limited to a particular domain. So, in ICOM, it's the U.S. East Coast, and GLM, it's the Great Lakes region in the U.S., and interface, it's the Arctic. So we can be asking scientific questions that don't require global information, but just require high resolution in the area of interest. One other advantage is that these smaller scale domains and then smaller scale processes, they have shorter spin up times. So, for example, where 5 years might not be sufficient to spin up the global ocean, a year is often sufficient for a spin up for most continental shelves. And many of these small scale processes don't influence larger scale, so nesting is often going to be okay. And so this is a much simpler approach, and we can downscale global ocean models to provide useful information for particular regions. And so that's kind of my first approach, my first point in talking about the relevance for E3SM. So this hierarchical approach of nesting and coupling ROMs within MPAS-O allows us to downscale for actionable projections. So we can better project climate signals in coastal regions, for example, marine heat waves, nutrient carbon cycling in river plumes or on the continental shelves. And these really require sort of high resolution, and they're important regionally for sure, sometimes important globally. But like say for marine heat waves, the U.S. East Coast, the continental shelf along the U.S. East Coast is heating up twice as fast as the rest of the Atlantic Ocean. And the processes that are driving this increased rate of heating are some of them are fairly large scale, but some of them are quite small. There's a recent paper that shows intrusions of warm water from warm core rings in the Gulf Stream that impinge on the shelf and introduce water in the lower continental shelf regions. And so this can be small scale processes can be really important in managing how heat is transferred onto the continental shelf and forming marine heat waves as an example. We also think that we can use these targeted, refined simulations for better process understanding. So, for example, biases in surface temperatures could be due to mis or underrepresented ocean processes, and local refinement can help identify these processes. Some of these things are being parameterized already, like Baylor Fox Kemper has a mixed layer restratification parameterization, but that's a parameterization that is may not be accurate in all situations. And we think that this could also be useful for more efficient simulations. If you don't have to run a 2 kilometer MPAS-O simulation with a long spin-up time, we can, at 10 kilometers, E3SM can run with targeted temporary nested grid refinement so that we can get to 1 kilometer space, sort of the state of the art for regional shelf modeling, for instance, much more quickly than we could if we tried to run everything at 1 kilometer. So, and looking forward to the future as E3SM transitions to GPU-enabled components, ROMS-X will allow us to continue this same approach using GPU-enabled configuration of ROMs. So those are some of the ways in which we connect to E3SM and help extend the predictive abilities to coastal regions. So I had promised to show you some other results. So this is a little bit off here. So this is a 1 kilometer simulation in the northern Gulf of Mexico. This is the Atchafalaya River plume you can see coming off here. And this is sea surface salinity. So you can see the freshwater plume here. And this is the relative vorticity normalized by F. And so this is the Rossby number. So this is a Rossby number of 2. It's quite energetic. So these are very nonlinear features. And we compared this model with observations that were randomly spaced. They were designed for benthic fish samples to see if we were getting the gradients right, over the salinity gradients right, because there are such a big range of gradients across the shelf, and we statistically matching these observations to the simulated salinity gradients, we get a pretty good agreement here. So we think that the model is, capturing the right scale of gradients in the plume. And here's an example of a nested model within that, two-way nested subdomain child model. And you can see here again is the sea surface salinity and the normalized relative vorticity. The features are even more energetic in this 300-meter simulation, and you start to see features along the fronts that weren't present before. We can compare this with observations in the Gulf Stream region from a study called LATMIX. And here are some observations of the strain rate normalized by F, the total strain rate normalized by F, and the relative vorticity normalized by F. And here are here's that same analysis done in a 500-meter ROMS simulation in that region with the normalized relative vorticity and strain rate. And you can see this is a lot noisier because it's difficult to get these observations. You need two ships to get the full velocity gradient tensor. It's easy to do in the model. You can see there's a lot of agreement between these, and there's a lot of agreement between this simulation and this. And so we think that these features are pretty ubiquitous. And once you start to resolve them, it doesn't matter if you're in the Gulf Stream, it doesn't matter if you're in the northern Gulf of Mexico, wherever you are, these features have the same sort of characteristics. They're basically sub-mesoscale features generated from baroclinic instabilities in larger scale flows. And so the dynamics are quite similar. So we've created an idealized channel flow simulation. So there's this is a reentrant channel that we're seeing here that's 300 kilometers across and reentrant in the X direction with walls to the north and south. And we started out very stratified and in a parameter space that is very much like this northern Gulf case. And we let it go unstable. And here you can see this is the Rossby number again, very nonlinear flows with eddy-like features everywhere. And this is an MPAS-O simulation and a ROMS simulation, both with a resolution of 1 kilometer. Now, this was our first attempt at this. I'll show you some more recent attempts later, but this is a histogram of the normalized relative vorticity within this domain here. And you can see while there's some small disagreement in the eddy regions, ROMS is a little more heterogeneous in the eddies, but not by much. In the frontal regions, which is this area over here, they actually match quite well. And you can see in the background here are these other lines are other cases with different resolutions. And so especially compared to these, they match quite well. Here is the surface divergence only in the area where the normalized relative vorticity is greater than 1. So we're sort of isolating the divergence at the fronts because fronts tend to be a region where there can be strong convergence and divergence. And so we can see that here, MPAS-O has slightly more points near 0, meaning it is not quite as it doesn't have the variability that ROMS does in divergence. But still, qualitatively is similar. But I think this is probably the biggest difference that we see is in the divergence field. This is the same plots, but for 5 kilometer resolution for MPAS-O. Now you can see the hexagons and squares, and you can see that they have similar-ish features. MPAS-O tends to have more circular eddies than ROMS does, and maybe slightly higher relative vorticity in the fronts. But when we do a histogram comparing these, you can see that they're, again, in the frontal regions similar, and in these flows that are less energetic, the divergence fields are a little closer to each other. Now these simulations were sort of our first cut. We have later done some comparisons where we've matched up the parameters more exactly between ROMS and MPAS-O, and strangely, they've started to diverge a little bit more. And so this is the 1 kilometer and 5 kilometer histograms of relative vorticity and the normalized divergence at the fronts. And you can see that the same thing is true about the divergence. MPAS-O seems to have a little more non-divergent flow than as compared to ROMS. And there are some slight differences in the histograms, but they are, for the 1 kilometer case, still skewed negative, which I think, and still pretty similar in the frontal regions. And the bigger difference is in the 5 kilometer case in this new configuration, where I think MPAS-O sort of went to what you might call a larger scale feeling flow with a more less skewed vorticity distribution. Did that earlier than ROMS, but if we compared that to a 10 kilometer case, ROMS would be quite similar to this MPAS-O case. They have similar, though there's differences here, they are more similar now in the eddy kinetic energy evolution. So we think that we still believe that the differences we're seeing are sort of details in the parameterizations, and matching the parameters up exactly between the models might not be the most appropriate. It might be that if you wanted the things to match exactly, you'd have to use slightly different parameters, all within the envelope of reasonable, though, because they're different models, and this is not really unexpected. So we have ways to compare these things robustly across different resolutions. This is a new way to analyze the flow at fronts using frontal coordinates and looking at the velocity gradients along the front, that's the y-axis, and across the front, that's the x-axis is along the front. The y-axis is across the front. This y-axis is exactly equivalent to the frontogenesis function, if you've ever heard of that. It is the tendency for the flow to intensify the front, and that's all this down here. So all these points in this 2D histogram are intensifying the front. These are frontalytic, destroying the front. And in the mean, you can see that there is a gentle compression of the front and no real along frontal velocity gradients, but the histogram spreads out quite a bit. And we believe this has to do, here is a 200 meter MPAS-O case, you can see, with extremely energetic flow and quite a bit of detailed instabilities forming along the fronts. This is really great. I think this is a spectacular simulation, and it's very similar to the ROMS results. And you can see what we have here is looking at the points in the front. You can see quite a bit of spread as we go to higher and higher and higher scales. That's all these little knots in the front. And as we go to coarser and coarser and coarser and coarser and coarser resolution, we go along, the points start to align along this line, which is the divergence equals 0, meaning that the flow, it doesn't have strong vertical components from the surface. And as you get more to submesoscale, you get much stronger vertical motions at the front. So this is a way we can quantitatively compare simulations across different resolutions in terms of these frontal processes. We are using MOAB. This is talking about the coupler work now to
Bob,
interpolate.
We're getting close to the end of the hour.
Okay. I can go over this very quickly. MOAB to interpolate. We're using splines, because if we do natural neighbor or locally conservative methods, it gets super noisy. So non-conservative local methods are what we have to do. Otherwise, the parent grid imprints too strongly on the interpolated grid. ROMS-X development. We are making good progress with this. It's a new code built on AMRX software, which allows for a lot of the grid decomposition to be taken by this general library. We have a lot of the base functionality built into ROMS, and we are working toward including more and more of the ROMS features. And preliminary results indicate weak scaling. So I think this means that we're doing a fairly good job of being able to use the GPUs efficiently. And we have various E3SM pull requests, so we're contributing back to E3SM free slip boundary conditions, optimization, time stepping coefficients. We have this idealized channel configuration that you can use if you want to study fronts, and we have a draft pull request for MOAB to do some of this coupling. And I'll put my conclusions up, and we can take questions.
Okay, great. Thank you.